Imagine a world where breathing could kill you. No blue sky, no fresh air, just a heavy, toxic atmosphere swirling with methane, carbon dioxide, and sulfur gas. The oceans shimmer red with iron, and the continents are bare, scorched rock. Now imagine that one day, something invisible starts to poison the planet. Tiny organisms smaller than a speck of dust begin to change everything. They don't mean to, but their waste becomes the most powerful and dangerous gas this world has ever known. Oxygen. This is the story of how air itself became a revolution, a story of death, ice, and rebirth. This is the Great Oxidation Event, when oxygen changed everything. More than 3.5 billion years ago, Earth was alive, but not as we know it. The planet's atmosphere was a strange, alien cocktail. There was no oxygen to breathe, no ozone to block deadly radiation, and certainly no animals or plants. The seas were full of strange microbes that lived off volcanic gases and minerals. They didn't need air, in fact, oxygen was their enemy. These were anaerobic organisms, thriving in darkness and chemical chaos. Volcanoes erupted endlessly, filling the skies with methane and carbon dioxide. The air was thick, the oceans hot and acidic. This was a world without breath. Then, something miraculous evolved: tiny bacteria capable of using sunlight in a brand new way. They were cyanobacteria, microscopic architects of destiny. They discovered a trick called oxygenic photosynthesis, splitting water molecules with sunlight to make food. But this new process had an unexpected byproduct: oxygen. Oxygen means life. To the early Earth, it meant destruction. At first, that oxygen didn't last. It was instantly absorbed, swallowed by iron in the oceans and minerals on land. For millions of years, it vanished as fast as it appeared. Still, the cyanobacteria didn't stop. They spread, quietly filling the seas with invisible, lethal gas. Slowly, steadily, the world's chemistry began to change. Around 2.4 billion years ago, oxygen finally escaped its prison. The oceans could no longer trap it, the rocks could no longer absorb it, and for the first time it leaked into the air. Earth took its first oxygenated breath. It happened slowly, over millions of years. But to the ancient world, it was an apocalypse. The very gas that fuels us today became the first poison, killing most of the anaerobic life that had ruled the planet. Entire ecosystems collapsed. This was the first mass extinction in Earth's history, all caused by oxygen. Scientists call this moment the Great Oxidation Event, but back then, it must have felt like the Great Dying. As oxygen rose, another tragedy unfolded. Methane, the greenhouse gas that kept Earth warm, reacted with the new oxygen, turning into carbon dioxide and water vapor. The planet's natural blanket was gone. Temperatures plummeted. Ice spread across continents, glaciers covered the seas, perhaps even reaching the equator. The Earth became a frozen marble, a snowball Earth. It was the planet's first great climate catastrophe, all triggered by the breath of bacteria. Oxygen had nearly killed the world. But beneath the ice, in the dark oceans, life held on, adapting, evolving, waiting. When the ice finally melted, Earth emerged transformed. The air now held a faint whisper of oxygen, still just a few % of what we breathe today. But enough to spark a revolution in biology. Life began experimenting. Some microbes learned to use oxygen, not fear it. They evolved powerful new metabolisms, aerobic respiration, unlocking 10 times more energy than before. That energy changed everything. It built bigger cells, more complex structures, and eventually the ancestors of all plants and animals. The Great Oxidation Event didn't just kill, it also created. It laid the foundation for every heartbeat, every breath, and every thought that would ever exist. So how do we know this story is true? The clues are written in stone, deep within ancient rocks. Scientists find banded iron formations, beautiful layers of red and silver iron that formed when oxygen reacted with dissolved iron in the oceans. They also find red beds, rust-colored rocks that appeared only after the atmosphere began to contain oxygen, and there's the mysterious sulfur signature. Ancient isotopes that vanish right at the moment oxygen became abundant together. These fingerprints tell us exactly when the air changed around 2.4 billion years ago. It was the day Earth's color palette shifted from gray to blue. Even after the Great Oxidation Event, oxygen levels remained low for nearly a billion years, an era scientists call the boring billion, but eventually, around 800 million years ago, oxygen surged again. This second wave, the Neoproterozoic oxygenation event, set the stage for complex life: sponges, jellyfish, worms, and the first animals without that ancient breath of oxygen. Evolution might have stalled forever. Every forest, every ocean creature, every human being owes their existence to the tiny cyanobacteria that once polluted the planet. But how exactly did oxygen win? Why then and not earlier? Some scientists think volcanoes changed, releasing fewer oxygen-consuming gases. Others point to the burial of carbon, locking away materials that would have otherwise eaten up oxygen. Maybe it was just a perfect storm, a balance of biology and geology that finally tipped the scale. Even now, researchers debate how long it took. Was it a quick rise over 10 million years or a slow dance over hundreds of millions? Every rock sample, every isotope clue brings us a step closer to understanding how life transformed its own planet. Today, we take oxygen for granted. But remember, it was once the most dangerous gas on Earth. It rusts metal, fuels fires, and corrodes everything it touches. Yet without it, our bodies wouldn't function for even a few minutes. The Great Oxidation Event reminds us that life and Earth are partners, constantly reshaping one another. Tiny bacteria changed the atmosphere, which changed the climate, which changed evolution itself. It's one of the greatest feedback loops in history, and we're still part of it. So next time you take a deep breath, remember that air carries the memory of ancient microbes. The same oxygen that fills your lungs once poisoned a world, froze the oceans, and gave birth to complex life. We are the children of that transformation, of that ancient chemical war. Oxygen changed everything, and in doing so, it made us possible. Picture a world without a single breath of oxygen. No blue skies, no green forests, no sound of waves washing upon the shore because there are no shores. Only endless oceans of iron-rich water, dark and heavy, covering most of the planet. This is Earth 4 billion years ago. A world alive, but not like ours. Back then, our planet was still young and restless. Volcanoes spat rivers of molten rock into the sky. Lightning struck constantly, dancing across thick, toxic clouds. The air was suffocating, a deadly soup of methane, ammonia, carbon dioxide, and sulfur gas. If you stood here, which you couldn't, the atmosphere would burn your lungs in seconds. It wasn't a world built for humans, or even for animals. Yet life had already begun. In the dark depths of those ancient oceans, microscopic life thrived, primitive, single-celled creatures. They lived without sunlight, feeding on minerals and chemical reactions from the seafloor. These were the archaea and anaerobic bacteria, the pioneers of existence. To them, oxygen was poison. It could destroy their fragile chemistry in moments. They had learned to survive in a world that was completely oxygen-free, a planet we now call the Archean Earth. Imagine, beneath thick layers of ocean, near volcanic vents, life pulsed like invisible sparks. These microbes clung to the rocks, feeding on hydrogen and sulfur, forming biofilms that looked like thin green mats. If you looked closely, the seafloor would shimmer a strange glow of activity. Invisible to the naked eye but teeming with ancient chemistry. Here, life found its rhythm, slowly evolving, one chemical reaction at a time. But all of this was happening in silence. There were no plants, no sounds, no oxygen to carry an echo. Just a quiet, alien world beneath red-tinted skies above. The young sun burned brighter than ever, yet Earth's thick methane-filled atmosphere trapped its light, turning the planet into a greenhouse of shadows and storms. The ocean waters were dark and murky, filled with dissolved iron that gave them a bloody red color. It was a place that looked more like Venus than the world we know today, but somewhere something was stirring. Tiny microbes, drifting closer to sunlight, began experimenting with a radical new way to survive. They discovered that light itself could be a source of energy, and that discovery would change everything. At first, it was just a mutation, a lucky accident. A few single-celled organisms developed pigments that could capture sunlight molecules, capable of turning light into power. These were the ancestors of cyanobacteria, the blue-green architects of the future. Unlike other microbes, these tiny cells didn't just use sunlight. They used it to split water molecules, releasing oxygen as waste that no one wanted. A toxic gas that could kill most living things on Earth at the time, but they kept going, multiplying, spreading, covering shallow seas with colonies of slimy mats. They worked silently, turning sunlight into energy and releasing oxygen one bubble at a time. They didn't know it, but they were changing the destiny of the planet. For millions of years, oxygen didn't accumulate in the air. It was immediately absorbed by the oceans, reacting with dissolved iron to form iron oxides, which settled on the seafloor. Layer after layer of these rusted sediments built up, forming what we now call banded iron formations, the ancient geological fingerprints of oxygen's first breath. Every band you see in those rocks today tells a story of how Earth slowly began to rust, and with that rust came transformation. Geologists have found these banded iron layers in places like Australia, Canada, and South Africa. They are 2.4 billion years old, marking the exact period when the Great Oxidation Event began. This was the first time in history that oxygen started to rise in Earth's atmosphere. Not much, but enough to change everything, enough to wipe out countless forms of early life, cause massive climate shifts, and reshape the chemistry of the entire planet. What began as a slow trickle became an unstoppable flood, a planetary scale oxygen revolution for the microbes that couldn't tolerate oxygen. It was the end of the world. Oxygen attacked their cells, breaking down their fragile molecules. For millions of years, mass extinctions swept across the oceans, but for a few, for the cyanobacteria and their descendants, it was a new dawn. They had evolved to live with oxygen, even use it. And in doing so, they changed Earth's destiny forever. The air around them thickened with this new gas. The sky, once red and hazy, began to turn blue. The seas cleared and sunlight began to penetrate deeper waters. The planet was becoming habitable, though not yet for us. Oxygen didn't just make the skies blue, it transformed chemistry itself. It allowed the formation of the ozone layer, which protected the surface from deadly ultraviolet rays. It gave rise to new forms of metabolism, allowing organisms to extract far more energy from food. This was the beginning of cellular respiration, the process that every human cell still uses today to stay alive, but at the time, it was just the start of something much bigger, a chain reaction that would, billions of years later, lead to plants, animals, and us. Still, for all its promise, oxygen remained rare for a long time. For nearly a billion years after it first appeared, the atmosphere hovered at only a fraction of today's levels. Earth was learning to breathe slowly. Cyanobacteria continued to produce oxygen, but the planet absorbed most of it into rocks and oceans. Only when those natural sinks filled up did oxygen begin to spill into the air, permanently changing the atmosphere, and when it did, the world would never be the same. As oxygen rose, the atmosphere cooled. Methane, once the main greenhouse gas, was destroyed by the new chemistry. Without it, Earth's temperature dropped drastically. The planet entered one of its deepest ice ages, possibly turning into a snowball Earth, but we'll get to that part of the story later. For now, imagine this moment, a young planet standing at the edge of transformation. A world filled with poisonous air slowly turning into the cradle of life. A silent revolution led by creatures smaller than a grain of dust, creatures that would make every breath of your life possible. Billions of years ago, sunlight touched the oceans of a restless earth, and for the first time, life looked up. It didn't have eyes. It didn't have a brain. But deep within the chemical machinery of a tiny cell, something extraordinary was happening, something that would turn light into life. This is the story of the cyanobacteria, Earth's first true architects. The tiny blue-green cells that built the world we breathe today. Imagine a time before plants, before animals, before oxygen itself. The seas were dark and full of iron, and the sky glowed orange-red with volcanic haze. In this strange alien ocean, a small group of microbes began to experiment with sunlight. Instead of hiding in the shadows, they rose toward the surface, toward danger, and then, by chance or by evolution's long patience, they discovered a trick so powerful it would rewrite the chemistry of the planet. They learned how to use sunlight to make their own food. We call this process photosynthesis, and it changed everything. Cyanobacteria were the first organisms to split water molecules using sunlight. In doing so, they extracted hydrogen to build sugar and released oxygen as waste, a waste product that was, for early Earth, lethal. These microbes, though it was freedom, no longer bound to volcanic vents or chemical energy, they could live anywhere the sun could reach. They spread across shallow seas, coating rocks and sand with thin green films, the first living carpets on Earth, and as they multiplied, their oxygen output grew, tiny bubbles rising from the sea like invisible breath. These colonies built structures we can still find today, stromatolites. If you visit Shark Bay in Australia, you can still see them, dome-shaped mounds rising from shallow water, alive with the descendants of the same microbes that once changed the world. Each layer represents generations of cyanobacteria living, growing, dying, trapping sediments, and building the first biological architecture on Earth. They were not only making oxygen, they were sculpting the surface of the planet. At first, the oxygen they produced didn't reach the air. The oceans were full of iron, which eagerly reacted with every molecule of oxygen, creating rust or iron oxide. This reaction turned Earth's oceans from murky green to deep red, a sign that oxygen was at work. It also left behind thick layers of banded iron formations, the geological records of Earth's first breath. But as the oceans ran out of iron, oxygen began to escape into the atmosphere. And once it did, there was no going back. To most ancient microbes, oxygen was a death sentence. It was highly reactive, tearing apart their delicate molecular structures. As oxygen levels climbed, vast populations of anaerobic life were wiped out. It was Earth's first mass extinction event, a quiet catastrophe in slow motion. But to the survivors, to the cyanobacteria, this new world was opportunity. They adapted, evolved, and flourished. Oxygen wasn't just waste anymore, it was power. In their tiny bodies, they discovered new ways to use oxygen to extract energy from food, leading to a process called aerobic respiration, a foundation of all complex life to come. With oxygen came a flood of biological possibilities. It allowed cells to generate far more energy than before, almost 20 times more than anaerobic methods. This surplus of energy became the spark that made complexity possible. Tiny organisms could now afford to grow larger, develop new parts, store more information, and build specialized systems. The stage was being set for multicellular life, though it would take hundreds of millions of years before that potential fully bloomed. But make no mistake, the oxygen revolution began here. With the cyanobacteria, let's pause and imagine what these early seas looked like. The surface glowed a hazy orange from methane-filled air. Beneath the waves, sunlight struggled through clouds of particles, and scattered across the seabed thousands of stromatolite domes, pulsing softly with life. Every bubble of oxygen they released rose to the surface and vanished into the unknown. Every layer they built was a new chapter in the story of Earth. If you could travel back to that time and stand in those waters, you'd be surrounded by the quiet rhythm of evolution, a world slowly preparing itself for breath. Cyanobacteria didn't just change the atmosphere, they changed evolution itself. Every plant you see today, every blade of grass, every leaf in a forest owes its existence to them. When plants evolved billions of years later, they inherited the photosynthetic machinery of cyanobacteria. In fact, the chloroplasts inside modern plant cells, the green structures that capture sunlight, are direct descendants of ancient cyanobacteria that once lived freely in the sea. That's right, every tree, every flower, every forest is carrying a piece of cyanobacteria inside it. Their legacy is alive in every living thing that breathes. We often call humans the engineers of the modern world, but cyanobacteria were the first true engineers of Earth. They built the atmosphere. They sculpted the environment. They turned a planet of death into a world of opportunity. They didn't plan it. They didn't know it. But through the slow, patient work of biology, they created the conditions for every creature that would ever live, and all of it started with a simple act: capturing light after hundreds of millions of years of photosynthesis. Oxygen levels finally reached a critical threshold. The chemistry of the atmosphere began to flip. Methane, the powerful greenhouse gas that had kept the Earth warm, was destroyed by oxygen's rise, and that triggered something new. Something dramatic, a world-changing cooling event. The very microbes that had warmed and transformed the planet now caused it to freeze. As methane vanished, sunlight reflected off the newly formed clouds, cooling the surface. Temperatures plummeted. Ice began to spread from the poles toward the equator. The world that cyanobacteria had filled with breath now began to hold its breath trapped beneath ice. But that's the paradox of evolution. The same process that creates life also brings destruction. And this time, oxygen, the gift of life, became a force of chaos. Still, cyanobacteria never stopped. Even during global freezes, they persisted beneath the ice, surviving in cracks, under glaciers, and in deep ocean layers. They were small, but they were unstoppable. They became the anchor of Earth's biosphere, surviving every catastrophe the planet threw at them. And through their persistence, oxygen kept flowing slowly, turning Earth into the breathable world we know even today. They continue their work, drifting through oceans, living in lakes, deserts, and even snow. Half of the oxygen you're breathing right now still comes from their modern descendants. Every breath you take is a whisper from the ancient seas. The cyanobacteria didn't just build the world, they built our world. They turned sunlight into life and death into possibility. They are the unseen architects of everything we are. But as their gift of oxygen transformed the planet, a new challenge began to unfold, one that would freeze the world to its core. Next, the story of the Great Oxidation Catastrophe. When oxygen's rise turned paradise into ice, the Earth had finally learned to breathe. Oxygen flowed through the oceans, drifted through the skies, and for the first time, the planet shimmered beneath a true blue dome. But what began as a miracle soon turned into catastrophe, because when oxygen rose, everything else began to fall apart. For billions of years, Earth had balanced on a delicate thread of chemistry. Methane, carbon dioxide, and water vapor, the greenhouse gases, wrapped the planet like a warm blanket. They trapped the sun's heat, keeping the oceans liquid and the climate stable enough for microbes to thrive. But oxygen changed everything. It reacted fiercely with methane, burning it away molecule by molecule. Methane, one of the strongest greenhouse gases, vanished from the air. And without that protective blanket, the world began to cool. Then freeze. At first, the change was slow, just a few degrees here and there. But over thousands, then millions of years, the ice crept outward. Glaciers formed near the poles, reflecting sunlight back into space, cooling the planet even more. It became a vicious cycle. The more the Earth froze, the less heat it absorbed and the colder it got. Eventually, the balance broke, and Earth plunged into the deepest freeze it had ever known. Imagine standing on the ancient shore 2.3 billion years ago. The horizon darkens, clouds thicken, and a sharp wind stings your face. Slowly, the waves begin to crystallize. Ice stretches out farther and farther, until the sea itself hardens into a mirror of blue-white glass. The entire planet from pole to equator becomes a frozen sphere, locked in ice for millions of years. Scientists call this period Snowball Earth, and it was one of the most extreme climate events in history. Temperatures plummeted to below 50 C in some regions. Even the equator saw glaciers a mile thick. Oceans were capped with ice hundreds of meters deep, sealing away the very sunlight that powered life. The Earth, once a living ocean world, had turned into a global cryosphere, a frozen tomb. And yet, paradoxically, this ice age was caused by life itself, the oxygen-producing cyanobacteria. Those ancient, blue-green architects had created the very conditions that nearly wiped them out. But life, even when cornered, finds a way beneath the crushing ice. In tiny pockets of brine and in the warmth of volcanic vents, microbial life persisted. These were extremophiles, organisms built to endure the impossible. They survived in geothermal oases, near undersea volcanoes where boiling water met frozen darkness. In these hidden realms, they continued to photosynthesize, feeding off dim light that filtered through cracks in the ice. They clung to life like whispers in the void. Slowly, oxygen continued to seep out, even in the cold. It didn't stop. It couldn't. The planet might have frozen, but the transformation was unstoppable. The Great Oxidation Event was still unfolding, shaping the air, the oceans, and the destiny of everything yet to come. Then, after millions of years of frozen stillness, the Earth began to stir again. Volcanoes, deep beneath the crust, molten rock built pressure, trapped under kilometers of glacial weight. Eventually, it burst free, erupting through the ice in cataclysmic explosions. Volcanoes spewed carbon dioxide, another greenhouse gas, back into the atmosphere, and for the first time in ages, the skies began to darken with volcanic haze. Slowly, painfully, the planet started to warm. The glaciers began to retreat, releasing rivers of meltwater that carried iron and sediment back into the seas after millions of years of silence. The Earth thawed, but this wasn't just a thaw, it was a rebirth. The end of Snowball Earth didn't simply return the planet to normal, it rewired it completely. Oxygen levels had stabilized. Carbon dioxide, once trapped beneath ice, mixed with the atmosphere again, restoring a gentler greenhouse balance. The oceans, churned by melting ice, became nutrient-rich, filled with minerals and elements like iron, phosphorus, and nitrogen. These were the building blocks of evolution. For the first time, life had access to both oxygen and nutrients in abundance. It was as if nature had reset the stage, clearing away the old world and preparing for something entirely new. Scientists call this period the post-Go biospheric revolution, and it would set the stage for one of the most extraordinary chapters in history: the rise of eukaryotic cells, the ancestors of all complex life before the freeze. Life had been simple, single-celled, self-contained, and slow to evolve. But after the Great Oxidation and the Snowball thaw, something miraculous happened. Cells began to cooperate. One cell engulfed another, not to eat it, but to live with it. Inside that partnership, a tiny symbiosis formed. The internalized cell could use oxygen efficiently, breaking down food into energy more powerfully than ever before. Over time, this partnership became permanent. That internalized cell evolved into what we now call the mitochondrion, the powerhouse of the cell. And its host became the first eukaryotic cell, the ancestor of plants, animals, and eventually us. It's no exaggeration to say that without oxygen, complex life would never have existed. The Great Oxidation Event didn't just change the chemistry of the planet, it changed the very architecture of biology. By the end of the Paleoproterozoic era, the Earth had survived one of the greatest catastrophes in its history, a self-inflicted ice age brought on by life's own success. But that catastrophe became creation. The air was no longer toxic. The oceans were cleaner, clearer, and filled with nutrients. The stage was set for the next great leap in evolution. When the ice melted, the planet gleamed beneath new blue skies, the first skies that truly resembled the ones we see today. And deep within the oceans, life stirred again, ready for another revolution. The world had been frozen, burned, and reborn. And all of it, every glacier, every volcanic eruption. Every living cell was a direct consequence of one thing: oxygen, even now, billions of years later. We can still see the scars of that frozen age. Geologists find evidence of ancient glaciers in rocks across Africa, North America, and Australia, layers of sediment known as tillites, marking the footprints of those ancient ice sheets. Banded iron formations, rusty stripes of red and gray, reveal the story of oxygen's first dance with iron in the oceans. Each layer is a page in Earth's diary, recording a time when life nearly destroyed itself only to emerge stronger. This is the irony of evolution. Progress often looks like disaster. The Great Oxidation Event and the Snowball Earth were not just planetary crises. They were evolution's crucible, a cosmic test that would decide whether life could adapt, innovate, and endure. It did, and because it did, we are here. The ice and the iron was not just a geological episode. It was the story of transformation, of a world learning balance. From suffocating methane skies to frozen oceans, to the rise of air fit for breathing, the Earth had taken its first painful steps toward becoming habitable. And now, with oxygen stable and the planet warming again, something extraordinary was about to unfold. The next chapter would see the rise of complexity, the birth of cooperation, and the first flickers of multicellular life. But before that, the Earth would test itself once more, because where there is oxygen, there is also fire. The ice had melted. The oceans were free again. The Earth, reborn from its frozen tomb, shimmered beneath a sky now rich with oxygen. But this was no longer the same planet that had frozen over eons ago. Something new was happening, something invisible yet unstoppable. Life was about to discover a secret that would change everything it meant to be alive. It was about to learn how to burn. When oxygen filled the atmosphere, it offered a new kind of power, one hidden in chemistry. Before, the earliest microbes relied on simple fermentation. They extracted energy slowly, inefficiently, from whatever organic molecules floated by. But oxygen, reactive, volatile, hungry, was different. It was like adding rocket fuel to biology. Organisms that learned to use it could break down food 16 times more efficiently than their ancestors ever could. They could grow faster, move faster, adapt faster. It was evolution's first superpower. This was the birth of aerobic respiration, a process that takes oxygen and converts it into energy. In the microscopic depths of the oceans, cells that had survived the Great Oxidation Event began to adapt. They found ways to coexist with oxygen, taming its destructive potential into a life-giving force inside these cells. Tiny molecular machines evolved, complex, elegant engines that took oxygen and turned it into pure energy. They were the mitochondria, the powerhouses of life, the descendants of ancient bacteria that had once feared oxygen, but now worshipped it. How did this happen? It began with an unlikely alliance. Somewhere around 2 billion years ago, a large single-celled organism engulfed a smaller one, a bacterium capable of harnessing oxygen's energy. But instead of digesting it, the host allowed it to live inside. In return, the smaller cell shared its power, its ability to burn oxygen efficiently. It was the first symbiosis, a partnership between two different forms of life. Over time, they became inseparable, evolving into a single, more advanced being. This new type of cell, the eukaryotic cell, was stronger, faster, and smarter. It had internal structures, compartments, and a nucleus to store its DNA. It could grow larger and perform more complex functions. This was the blueprint for all complex life, from plants to animals, and eventually humans. Every breath we take today is a continuation of that ancient alliance, a pact made between two microscopic entities billions of years ago, but oxygen was not just a blessing. It was dangerous, a volatile element that could destroy as easily as it could empower. To harness it, life had to evolve defenses. Free radicals, unstable molecules formed during oxygen metabolism, could rip through DNA, proteins, and membranes. Cells had to develop antioxidants, repair systems, and protective enzymes just to survive their own energy production. It was as if evolution had handed life a torch, one that could light the way forward, but also burn everything it touched, yet life adapted. And in doing so, it unlocked a kind of resilience the planet had never seen before. With oxygen stable and abundant, the chemistry of the oceans began to change dramatically. Iron, once dissolved freely in the seas, now rusted and sank to the bottom, forming thick layers of banded iron rock. The once green waters turned a deep, rich blue, the first true blue oceans in Earth's history. This was the birth of the modern ocean, clear and oxygenated. It became a cradle for new kinds of life, larger, more complex cells that began to experiment with form and function. Some formed colonies. Others began to communicate chemically, sharing nutrients and signals. The groundwork for multicellularity was being laid for the first time. Evolution wasn't just about survival, it was about potential. But oxygen didn't just change life, it changed the planet itself for the first time. The atmosphere became rich enough to support fire. Before the Great Oxidation Event, you could have struck 1,000 lightning bolts on dry land, and not a single flame would have caught. There simply wasn't enough oxygen to feed combustion. Now, with oxygen levels rising past 10%, the world had crossed the fire threshold. Lightning could ignite wildfires. The air could burn. Imagine the first flames licking across a barren landscape, no trees yet, no grasses, just dry mineral crusts and primitive microbial mats. The planet itself was learning to breathe and burn. Fire became nature's purifier. It cleared carbon, recycled nutrients, and forged new minerals. It was destructive, yes, but it was also a creative force, setting the stage for the next phase of evolution. As oxygen levels climbed and fell over millions of years, the Earth entered cycles of stability and chaos. Sometimes oxygen would spike, fueling massive blooms of new life. Other times it would crash, plunging the planet back into low oxygen conditions, triggering die-offs. Scientists call these oxygen overshoot events. They were like nature's growing pains, a planet learning how to balance breath and flame. Each pulse of oxygen brought both progress and peril. But through it all, one truth emerged. Life and oxygen were now forever linked, locked in a feedback loop of creation and destruction, even as Earth transformed. The true architects of oxygen, the Cyanobacteria, continued their quiet work. For billions of years, they had been the unseen engineers behind every major shift in the planet's history. They coated shallow seas, built stromatolites, and kept releasing oxygen, molecule by molecule. They were, in essence, the lungs of the planet, and their legacy continues even today. In the chloroplasts of plants, tiny green descendants that perform the same ancient photosynthesis. When you walk through a forest and breathe in the scent of leaves and earth, you're inhaling the story of cyanobacteria, the same process that once turned a toxic world into a living one. As life grew more complex, competition for energy became fierce. Organisms that mastered oxygen metabolism thrived. Those that didn't vanished. This was evolution's quiet war, a microscopic battle fought in the depths of oceans, cell by cell. But out of this struggle, something beautiful happened: diversity. Different species evolved different strategies. Some used sunlight, others used oxygen. Some even found balance between the two. It was in this chaos that innovation was born. The rules of survival had changed forever. The age of simplicity was over, and the age of complex life was dawning. It's astonishing to think, a simple chemical reaction, the union of oxygen and carbon, became the driving force behind everything we know. Stars burn hydrogen, planets burn carbon, and we, living beings, burn oxygen from the smallest cell to the largest star. Fire is the common language of the universe. Oxygen gave Earth the ability to host fire and metabolism to power storms, weather, and life itself. It made our planet dynamic, restless, and alive. Without oxygen, there would be no heartbeat, no movement, no thought. Just silence. By 1.8 billion years ago, oxygen had stabilized at moderate levels. The Earth was now a living world, breathing, cycling, and evolving. But for all its change, one thing was still missing: true complexity. Multicellular life, animals, plants, ecosystems had yet to appear. The stage was set, but the actors were not ready. The planet had the tools: oxygen, nutrients, and energy, but it needed something more: organization. The kind of biological cooperation that would take life from single cells to societies of cells, and soon that leap would come. Because deep in the oceans, colonies of cells were learning something new: how to live together. The fire within had burned bright enough to awaken not just life, but intelligence. The oceans had calmed. The Earth was warm again. Oxygen flowed freely through the sky and sea, no longer poison, no longer chaos, but the quiet pulse of a living planet. The Great Oxidation Event had come and gone. The age of fire had reshaped the world, and now something incredible was stirring beneath the waves. Tiny cells, once lonely and independent, began to gather, forming colonies, then tissues, then the first fragile bodies. For the first time in the planet's 4 billion-year history, life was learning how to cooperate. It started small. Individual cells began sticking together after division instead of drifting apart. They shared nutrients, exchanged signals, and divided tasks among themselves. Some specialized in capturing food, others in movement, others in defense. It was evolution's first experiment in teamwork, a radical idea: survival not as one, but as many. This was the birth of multicellular life. And oxygen was the reason it was possible. In the oxygen-poor world before, cells couldn't generate enough energy to support complex structures. But with oxygen, they could build bigger bodies, stronger membranes, and longer lifespans. It was like upgrading from a candle flame to a lightning storm. Every cell is a miniature city with factories, power plants, transport systems, and waste control. But all of that requires energy. Lots of it. Oxygen made that possible through aerobic respiration. Life could now extract enormous amounts of energy from food, enough to power communication between cells, create tissues, and eventually form organs. Oxygen became the silent architect of complexity. It didn't just give life more power, it gave it purpose: the ability to build, to specialize, to evolve beyond the limits of chemistry. But evolution never rushes. For nearly 1 billion years after the Great Oxidation Event, the Earth entered a strange, quiet age. Scientists call it the boring billion, between 1.8 and 0.8 billion years ago. Oxygen levels stayed stable but relatively low, just enough for simple eukaryotes, but not yet enough for animals. The climate was calm. The continents barely moved. The oceans were peaceful, green, and full of microbial mats. Life seemed content. It grew, diversified microscopically, and waited. But in that stillness, profound things were happening. Genetic complexity was increasing. Cells were experimenting, developing communication systems, reproductive cycles, and early immune defenses. They were preparing for something enormous. The world looked boring, but beneath the surface, evolution was sharpening its tools. Around 800 million years ago, the peace ended, tectonic plates shifted, volcanoes roared, and the oceans churned. Nutrients from the deep, iron, phosphorus, and nitrogen, surged upward, feeding cyanobacteria in explosive blooms. Oxygen levels began to rise again, a second oxygenation event. This was the spark the planet had been waiting for. Suddenly, oxygen flooded the atmosphere and seas once more, reaching levels similar to today's around 10%. And this time, instead of freezing the world, it ignited it. With so much oxygen available, metabolism accelerated. Cells grew larger. Colonies evolved into organized bodies. The first true multicellular organisms appeared soft, simple, and strange. They were the ancestors of everything that breathes today. They lived in shallow seas, thin, ghostly forms swaying in the currents. They had no bones, no shells, no eyes, but they were alive in a new way, coordinated, structured, and purposeful. This was the Ediacaran period, the twilight before the Cambrian explosion, and its inhabitants were some of the most mysterious creatures ever to exist. Some looked like giant leaves anchored to the seabed, the Charnia. Others resembled quilts or fractal discs, Dickinsonia, perhaps one of the earliest animals. Some crawled, some filtered water. Some just absorbed nutrients through their skin. They were alien, beautiful, and utterly new, the first multicellular experiment of nature. Without oxygen, none of this could have happened. Complex life needs energy density, and oxygen provides that in abundance. For perspective, one molecule of glucose yields only 2 ATP energy units without oxygen. With oxygen, it yields 36 ATP, 18 times more. That difference is what allowed cells to grow larger, build tissues, and sustain movement. It's the reason your heart can beat 100,000 times a day. It's the reason your brain, which uses 20% of your body's oxygen, can think, dream, and create. All of it began here in those ancient oceans. When cells first learned to breathe together, as oxygen levels climbed, the planet itself changed color. Iron in the oceans oxidized out, leaving the waters clearer and bluer. The sky, rich in ozone, became a shield against ultraviolet radiation, protecting life from deadly solar rays. Land surfaces rusted red as iron minerals oxidized. Even the chemistry of weather changed, with new minerals forming, new soil types emerging, and atmospheric pressure stabilizing. The Earth was no longer just habitable. It was home. Once multicellular life emerged, communication became the next frontier. Cells began using chemical signals to coordinate proteins, hormones, and neurotransmitters. This was the birth of the first primitive nervous systems. Some colonies began pulsing rhythmically, coordinating contractions. Others developed light sensitivity, allowing them to detect day and night. These were the first steps toward intelligence, the faint sparks that would one day become thought. Oxygen wasn't just fueling bodies, it was fueling minds. But evolution is never smooth. Around 720 million years ago, another global ice age struck, a second snowball Earth, triggered partly by shifts in oxygen and carbon cycles. Once again, glaciers covered the planet. And once again, life retreated beneath the ice, to hydrothermal vents, to cracks in the seafloor, to refuges where oxygen could still flow. But when the ice melted, something extraordinary happened. The world that thawed was full of oxygen, nutrients, and open ecological space, and into that space, evolution exploded. The multicellular forms of the Ediacaran were just the beginning. By 540 million years ago, a new chapter was ready to unfold, the Cambrian explosion, when almost every major animal group appeared in a geological instant. Skeletons formed. Eyes evolved. Predators hunted. Ecosystems emerged. The quiet earth of microbes had become a planet of movement, competition, and wonder. And oxygen, the same invisible gas that once poisoned the world, had made it all possible. The first breath of multicellular life had changed the story of the universe. From here on out, evolution would never look back. Look around you. Every tree, every animal, every human being, every breath you take is a continuation of that first oxygen revolution. Our blood carries oxygen in iron-based hemoglobin, echoing the iron oceans of ancient Earth. Our lungs replicate the chemistry of those early cyanobacteria, pulling oxygen from air and releasing carbon dioxide in return. Even our mitochondria, the descendants of ancient symbionts, still burn oxygen to power every heartbeat. We are walking monuments to the Great Oxidation Event, living fossils of a 2.4 billion year old experiment, and yet, the story isn't over, because oxygen, for all its gifts, also carries a warning. The same volatile, reactive force that created life still has the power to destroy it. The balance must be kept, always, from a world without air to a planet alive with breath. The Great Oxidation Event didn't just give Earth an atmosphere, it gave it a soul, and that soul, made of fire and air, was ready for its next great trial: oxygen, the gas that gave life its breath. Now it would teach life about death. For millions of years, oxygen had been a miracle, the energy source that powered evolution from single cells to complex organisms. But oxygen was never gentle. It was and still is a reactive, corrosive force, and in the ancient world, that force would nearly end everything it had created. To us, oxygen means life. But to early life it was poison. Even now, oxygen slowly destroys us, aging our cells, burning through our DNA, and corroding the very molecules that sustain us. We've simply learned to survive it. For a time, billions of years ago, when oxygen first appeared, most organisms didn't have the tools to handle it. They were anaerobic, built to live in a world without free oxygen. When the Great Oxidation Event filled the air with O, it didn't just change the chemistry of the planet, it triggered the first great extinction. The very element that made Earth habitable for some made it uninhabitable for others. It began quietly. Oxygen levels rose, creeping into every ocean current, every tide pool, every volcanic vent. Anaerobic microbes, the dominant life forms for 2 billion years, began to die out. Their enzymes were destroyed by oxygen's reactivity. Their metabolic systems failed. Whole microbial ecosystems vanished, leaving behind barren, rust-stained seafloors. It was an invisible apocalypse. No comets, no volcanoes, no fire. Just the slow suffocation of a world that could no longer breathe its own air. Some scientists estimate that over 90% of Earth's species perished in this oxygen catastrophe. Only those that could adapt or hide survived. Life's answer to oxygen was one of evolution's greatest tricks: mitochondria. In the chaos of the oxygen apocalypse, some cells found a way to coexist with oxygen rather than avoid it. They formed partnerships, symbiotic mergers between ancient anaerobes and oxygen-loving bacteria. These bacteria became the mitochondria, the power plants inside our cells today. They took in oxygen, burned nutrients, and produced energy safely. It was nature's solution to the oxygen crisis, turning poison into power. This evolutionary leap gave rise to eukaryotes, complex cells that could survive in oxygen-rich environments. It was a masterstroke of survival, the blueprint for all higher life. But oxygen didn't just attack life, it attacked the planet itself. Iron, once dissolved freely in the oceans, began reacting with oxygen to form rust, sinking to the seafloor as banded iron formations. The oceans turned red, then clear. Methane, a powerful greenhouse gas, reacted with oxygen to form coal and water, cooling the planet. The world entered its first global ice age. For tens of millions of years, glaciers stretched from pole to equator, a frozen Earth. This was Snowball Earth, a planet nearly sealed in ice. Life clung to survival beneath the frozen surface near volcanic vents, geothermal pools, and thin cracks of light beneath the glaciers. Oxygen had reshaped the world not only biologically, but geologically. It was both the sculptor and the storm, yet even as Earth froze, evolution was at work beneath the ice. The survivors, extremophiles, adapted to oxygen and cold alike. They learned resilience, flexibility, and cooperation. When the ice finally melted, the Earth awoke, reborn. The melting glaciers flooded the seas with minerals. Oxygen levels stabilized, and the survivors emerged stronger, ready to build the first multicellular ecosystems. Out of catastrophe came complexity. Out of extinction came innovation. This would become a pattern repeated throughout Earth's history. Every mass extinction resets the game and evolution plays again. Smarter than before, oxygen didn't stop being dangerous once life adapted. Even today, every breath we take is a controlled burn inside our cells. Oxygen drives metabolism, but it also creates free radicals, unstable molecules that can rip through DNA, damage membranes, and kill cells. We've evolved defenses, antioxidants, repair enzymes, immune systems, but the cost of oxygen metabolism is inevitable decay. Aging is, in many ways, the price of oxygen. To live is to slowly burn, yet that same combustion fuels everything: thought, movement, emotion. Oxygen is both our destroyer and our lifeline. It is the paradox of life itself. We live because we die. We die because we live. Oxygen's toxicity sparked an evolutionary arms race. Organisms that could handle it thrived. Those that couldn't vanished. Cells developed new defenses. Catalase and superoxide dismutase enzymes that neutralize oxygen. Radicals, protective membranes that limit oxygen. Diffusion, DNA repair mechanisms to fix oxidative damage. This invisible war-shaped evolution at its core. Even the structure of DNA, the double helix, may have evolved as a defense against oxygen's destructive chemistry. Providing stability and redundancy in a volatile environment, oxygen wasn't just fueling evolution, it was driving it through destruction hundreds of millions of years later. Oxygen would again play its dark card. During the Neoproterozoic era, volcanic activity, tectonic shifts, and biological feedback loops drove oxygen and carbon dioxide levels into chaos. Once more, the world froze solid. Ice stretched across continents. The seas were locked under miles of frozen water. Photosynthesis faltered. Food chains collapsed. It seemed life had reached its end, but deep beneath the ice, around volcanic vents, oxygen-fed bacteria persisted. They became the seeds of rebirth. When the glaciers finally retreated, oxygen surged back, and with it came a new wave of multicellular life. This set the stage for the Cambrian explosion, the greatest burst of evolution in Earth's history. Oxygen had destroyed, yet it had also prepared. Even after billions of years, oxygen levels still rise and fall, controlled by the dance between biology and geology. Too little oxygen and complex life suffocates. Too much and the planet burns. At certain points in history, like the Carboniferous period, oxygen levels spiked to nearly 35%. In those days, insects the size of eagles and dragonflies with 2-foot wingspans ruled the skies. Fires raged across continents, fueled by oxygen-rich air. When oxygen dropped again, those giants vanished. The balance between oxygen and carbon has always been the heartbeat of Earth, the silent rhythm guiding evolution. Oxygen brings another power, one no other gas in the universe can match. Fire. Before oxygen, fire was impossible. After oxygen, fire became nature's sculpting tool. It cleared forests, reset ecosystems, and shaped the rise and fall of species. Even early humans would one day harness it, using the same oxygen that once froze the planet to warm their caves and cook their food. Fire is oxygen's visible form, the breath of life turned into light. The irony is cosmic. The element that nearly destroyed Earth's biosphere became the one that illuminated the night when animals evolved. Oxygen shaped them to transport this volatile gas safely. Evolution invented blood, a liquid highway filled with specialized molecules. Iron-based hemoglobin binds oxygen in vertebrates. Copper-based hemocyanin serves in some invertebrates. The red color of our blood is a reminder of those ancient trusting oceans, a chemical echo of the Great Oxidation Event. We carry the planet's transformation inside us. Every breath you take today, every beat of your heart, is a continuation of that ancient war between oxygen and life. Oxygen's story is not a simple tale of good or evil. It is the story of balance, of creation through destruction, of fragility through power. The same molecule that enables consciousness can also erase it in moments. The same process that builds ecosystems can collapse them through fire or ice. Life on Earth learned this balance the hard way, through extinction, through survival, through adaptation. And that balance between oxygen's shadow and light is what keeps this planet alive today. If you look at Earth from space, it glows blue, the color of oxygen's gift to the cosmos. No other planet we know of breathes like ours. But beneath that beauty lies a constant tension. Too little oxygen and life fades. Too much and it burns away. That balance, fragile and invisible, defines everything we are. We walk a line drawn billions of years ago by bacteria, by fire, by ice. The line between life and death, between breath and silence, and it all began when oxygen, for the first time, filled the sky. Oxygen gave us the power to live. It also gave us the destiny to die. Yet through that fragile balance, it gave the universe something it had never seen before: awareness, a living planet that could think, a species that could wonder where it came from, a world that could breathe and in that breath tell its own story. Billions of years after oxygen first appeared, the world was still quiet but no longer dead. The planet had endured fire, ice, and poison. The air was now rich. The oceans oxygenated and deep within them. Something extraordinary was about to stir after eons of stillness. The earth was preparing for motion. This was not just the rise of animals. It was the awakening of sight, hunger, and consciousness, the first flicker of the modern world. The time was about 600 million years ago, during the Ediacaran period. For billions of years, life had been microscopic tiny cells drifting through water, unseen and simple. But now the world's oxygen levels had finally reached a threshold, roughly 10% of what we breathe today. It doesn't sound like much, but that was enough to ignite complexity. With oxygen came energy. Cells could burn fuel more efficiently. They could grow, divide, specialize, build tissues, muscles, and nervous systems for the first time. Life could afford to move. Imagine walking along the seafloor 600 million years ago, if you could walk at all. There are no fish, no shells, no bones. Just soft-bodied creatures carpeting the ocean floor like living quilts. These were the Ediacaran biota, strange alien organisms that defy easy description. Some looked like ferns pressed flat against the sand. Others resembled giant leaves or rippling discs. There were no mouths, no eyes, no stomachs, just forms, absorbing nutrients through their skins. They lived in peace, drifting in slow motion. A world before fear, before predation. A silent garden beneath a dim sun. But change was coming, and oxygen was the fuse. As oxygen levels continued to rise, evolution began experimenting. Some organisms developed the first muscle-like tissues, allowing them to flex and crawl. Others evolved simple nerve networks, the ancestors of brains, and then something happened that changed everything forever: the invention of vision. Tiny patches of light-sensitive cells evolved, primitive eyes that could detect brightness and shadow. For the first time, life could see. With sight came awareness, and with awareness came hunting. The age of innocence was over, roughly 540 million years ago. Oxygen levels rose again, enough to supercharge evolution. In what scientists call the Cambrian explosion, life diversified at a pace never seen before. In a geological instant, perhaps 20 million years, the oceans filled with creatures of staggering variety. Predators and prey, hunters and hiders, swimmers, crawlers, burrowers, and floaters. It was life's arms race, powered by oxygen. With more oxygen in the water, metabolism surged. Muscles grew stronger. Nervous systems expanded. Shells hardened. Eyes sharpened. Creatures became faster, smarter, deadlier. The earth had gone from microbial stillness to a teeming, moving, blinking world. Oxygen didn't just fuel motion, it enabled defense. To survive predators, Creatures evolved shells, spines, and teeth. Calcium, once dissolved freely in the oceans, was now used to build protection. Trilobite cyconic creatures of the Cambrian developed hard exoskeletons and complex eyes with thousands of lenses. They could see in multiple directions, detect movement, and react instantly. Vision had turned the ocean into a battleground of awareness, and every new predator forced prey to evolve faster. This evolutionary feedback loop called coevolution created diversity on a scale the world had never known. The brain, that mysterious command center, is one of oxygen's greatest inventions. Brains are energy-hungry organs. They consume massive amounts of oxygen to process information, sense danger, and make choices. Before oxygen, such energy-intensive organs were impossible. But now the stage was set for intelligence. Creatures like Anomalocaris, a top predator of the Cambrian seas, had complex eyes, fast reflexes, and coordinated attacks. These were the first hunters with strategy. Every movement, every chase, every flick of a fin or bite of a jaw, all powered by oxygen.it, was evolution's first glimpse of thinking life. Scientists believe that higher oxygen levels didn't just enable large bodies, they also encouraged specialization. Multicellular organisms could afford to evolve organs that performed different tasks. Some cells focused on movement, others on digestion or reproduction. Oxygen allowed division of labor within a body, turning simple clusters of cells into organized creatures. This is the essence of complex life: cooperation, fueled by oxygen's energy. Without that chemical fire, complexity would have never taken hold. Earth would have remained a microbial world, quiet, timeless, unseen. The Cambrian seas must have been astonishing, shimmering with movement, colors, and new forms. Worms tunneled through sediments. Jellyfish-like creatures drifted near the surface. Early arthropods scuttled along the bottom, their shells glinting in the filtered sunlight. The once silent ocean now roared with motion. For the first time, the planet had an ecosystem, a web of life where energy flowed from prey to predator. From algae to scavenger, oxygen had created not just life but interconnected life, and in doing so, it gave rise to the very first food chains, the first struggles for survival, and the first spark of behavior above the water. The land was still barren, scorched rock, wind, and dust, but the air above it was now breathable. The same oxygen that filled the oceans was escaping into the sky, forming an invisible ozone layer that shielded Earth from deadly ultraviolet radiation. That protective layer was crucial. Without it, no life could ever crawl onto land. So oxygen didn't just change biology, it prepared the stage for the future. For plants, animals, forests, and eventually humans. Every green leaf that grows today owes its color to oxygen's legacy. Every breath we take is the echo of that ancient transformation. It's almost poetic. The same element that once suffocated life became the foundation of intelligence. Without oxygen, our neurons couldn't fire, our muscles couldn't contract, our brains couldn't dream. Everything that defines us, language, memory, art, thought, depends on oxygen's chemical energy. Even the spark of consciousness itself may trace back to the first creature that sensed light and moved toward it. From that single act, movement guided by awareness, came everything we are today. The Great Oxidation Event was not just a planetary change, it was a cosmic turning point. It transformed a lifeless rock into a biosphere. It turned chemistry into biology, and billions of years later, it turned biology into consciousness. Every sunrise you see is painted by oxygen scattering light. Every forest breathes because of it. And every human story, every word, every song is powered by the same molecule that once nearly ended all life. The Great Oxidation Event wasn't a moment. It was a rebirth, the Earth reinventing itself. Think of it this way: every oxygen atom in your body, every molecule in your lungs has existed for billions of years. It once rusted ancient oceans, froze continents, fueled microbial wars, and drifted through the first living cells. When you breathe, you're inhaling history. When you exhale, you're returning it to the planet. You are part of a cycle older than the stars, the eternal rhythm of oxygen and life. Oxygen didn't just change the Earth, it changed the story of the universe itself. No other planet we know of breathes. No other world carries life so deeply intertwined with its atmosphere. If aliens ever find Earth, they'll know we exist before they see us by the oxygen glow in our sky. That signature, written in light, is the mark of life. It's the fingerprint of a planet that learned to breathe. So when you take your next breath, remember this: you are inhaling the memory of the Great Oxidation Event, the moment when the Earth first opened its lungs to the cosmos. That breath connects you to everything that ever lived. It's the same air that powered the first fish, the first forest, the first flame, and the first human thought. Oxygen changed everything, not just the planet, but the very meaning of life. And in the quiet rhythm of your breath, the ancient world still whispers, I am the air that made you.